Oh, I guess the microphone is on. So I'd like to thank the organizers for the invitation. It's a beautiful new conference center, and happy for the opportunity to have some better weather in kind of early spring than what I'm used to, or what I should have in New York and New Jersey. So this is my title. So minimal surfaces in CH2 and their Higgs bundles. Okay. So I guess the work that I'll talk about is recent work which is joint with Ian McIntosh from the University of York. Okay, so So I guess we've studied kind of some of these minimal surfaces. So this is the CH2 is the complex hyperbolic plane. We've studied them for a while, but it turns out that there's kind of if you bring in the Higgs bundle theory in the right way, then there's kind of a very nice way of describing all equivariant minimal surfaces into CH2 in terms of some algebraic data. And so that's what I'd like to discuss, is kind of this recent theory, this recent theorem with McIntosh. And so, yeah. Question? Yes, these are going to be equivariant under a compact surface group. Yeah, so I'll explain. So so I guess I'm kind of coming more from geometric analysis and differential geometry, and I'm still, at some point I'm going to have to stop saying this, but I'm still somewhat new to Higgs bundles, especially compared to a lot of the people here. But it turns out that it's kind of, for this problem, it's quite a very powerful technique, and you can kind of write things down in a fairly complete manner. Okay? So let me, so can people see this? Is this big enough? Okay, so I'll try to kind of remain. So what I'd like to kind of start out with in this talk is I'm going to state the theorem, and then I'll explain the terms in the theorem. And then I'll talk about kind of Higgs bundles. So these are going to be over Riemann surfaces for the group. I guess we'll start out with U21, and then I guess PU21 is the set of holomorphic isometries of CH2. And then say a little bit about minimal surfaces and how they relate to Higgs bundles in this case. And then some previous results and some geometry related to this. And I guess, so the last thing is how to relate this to, in some cases, to the geometry of surface group representations with kind of a higher Teichmuller theory type things. But the result itself is kind of mainly a differential geometric result. So we'll have a classification theorem for all of these minimal surfaces which are equivariant in the correct way. Okay, so so I guess the first thing is I'll state the theorem, which was completed last year. So so let sigma be a closed oriented surface of genus, of course, bigger than or equal to 2. And we're going to consider a representation of this surface into PU21, the set of holomorphic isometries of CH2. And I want to assume this is going to be irreducible, which is the standard assumption for Higgs bundle theory. And we're going to have a map of the unit disk into CH2, and F from the unit disk into CH2, a minimal branched immersion. So in particular, generically it's just going to be a minimal immersion, but we can handle the case of branch points, which comes up often in minimal surfaces of higher codimension, and which is rho equivariant. So these two assumptions together mean that we're really considering kind of some structure on this closed Riemann surface, and we're kind of, in some sense, kind of thickening this structure, at least locally, to have a, to embed the surface in a quotient of CH2, only a local quotient of CH2, by the image of this group. And I guess when I say quotient of CH2, I'm lying a little bit because we don't know in general that this kind of representation is going to be very nice at all. In general, it may not be properly discontinuous, or and so it may be quite nasty. But we can handle kind of all of these things as long as it's irreducible. Okay. Okay, and so we're going to make an additional kind of assumption. So we're going to assume. So this is going to be a generic assumption. So that F is neither holomorphic nor anti-holomorphic. Okay? So we're considering kind of these as real embeddings. So we are going to have a, so this is kind of as a map of the unit disk. Then under this situation, the set of such rho comma f, where you mod out by the natural action of PU21, so PU21 translates F in CH2, and then kind of there's a global conjugation on the image to act on rho. So this set is equivalent to the following set. So, let's see, so that's already a typo. So we're going to have, so what this is going to be a, so this is going to be an element of the Teichmuller space of sigma. So this is going to be a Riemann surface, or a conformal structure on sigma. So I denote kind of the conformal structure as C. So C kind of parametrizes the points in Teichmuller space. So D1 and D2 are going to be non-negative divisors. On this Riemann surface with degrees that are going to be small d1 and d2, small d2, such that 2 small d1 plus d2 is less than 6 times g minus 1, and similarly d1 plus 2 times d2 is also less than 6g minus 1. So d1 and d2, these are just the degrees of these divisors. Okay? All right. And similarly, this C is also going to be an element here. So C is going to be an element of this following cohomology group. So on the Riemann surface, we're going to consider the line bundle, which is going to be the negative 2 power of the canonical bundle, then modified by D1, or twisted by D1 plus D2. Okay? So what's happening here is that this cohomology class we think of as an extension class for the following sequence of bundles. Okay. So these two are line bundles. So this is going to be the anti-canonical bundle twisted with D1, and this is going to be the canonical bundle twisted with minus D2. And then we're going to make a rank 2 bundle out of this. And the number of ways you can, and so of course in general this is not going to be a splitting, and the classification of the number of ways that you can do this up to isomorphism is exactly given by elements of this cohomology class. And so you can think of, I mean, this part is just exactly this line bundle tensor the dual of that line bundle. So this is going to be this cohomology class. Okay, so I guess to kind of continue the theorem, so in all cases, there's an invariant for these sorts of representations, rho, this Toledo invariant. So tau of rho is given by a formula. So it's essentially just the difference between the the degrees of these divisors up to this power of 2/3, and the Euler number of the normal bundle of F is 2 times G minus 1 minus D1 minus D2, okay? So the degrees of these divisors kind of determine are equivalent to these two pieces of data for the representation, these topological pieces. The Toledo invariant and this Euler number of the normal bundle. The maximal Toledo invariant, those are all holomorphic or anti-holomorphic, but there are also other ones for other values of the Toledo invariant. There are also holomorphic examples. So I guess I should remark that so this I think of as kind of our main theorem, but we can handle the holomorphic and anti-holomorphic case. And you get kind of a similar description, but I mean, there aren't going to be these divisors. These divisors are really kind of depend on the real theory. You get a similar description in this case. And I guess also you can handle, so in this case you have this is going to be an equivariant minimal surface. And so in particular, you actually, this kind of translates into a special case of, I guess, this sort of Hermitian-Yang-Mills object here. And so in general, I guess there's a theorem of Corlett that in general, if you have this sort of representation together with this minimal surface data, then it's going to be, I guess, what do you call I guess the right word is reductive, but kind of on the Higgs bundle side, this is going to the strictly polystable case. And also the non-irreducible case. And kind of the reason for the non-irreducible case is, so if you have the non-irreducible case and you have this branched minimal immersion, in particular, what happens is you're going to have a splitting of kind of a natural vector bundle. So this is going to be a rank 3 vector bundle for this case, and this group means that there's already a lot of structure here. And so the sorts of splittings that are possible are very limited, and we can just analyze those because they're easier. So the non-irreducible case is easier, so that's not kind of really a problem. Yeah, question. Yes, so it's kind of towards the end when I talk about kind of the geometry of representations, I mean, we do have some examples in the case where this minimal surface is Lagrangian, under which we can kind of actually, we can show that the representation is discrete and faithful. And essentially what we do is we can show that if you have this, this immersed surface, we can actually show that the natural immersion of the normal bundle, which in this case is going to be by Lagrangian planes, is covered by CH2 under some situations. But that requires some estimates, some kind of C0 estimates of say, the second fundamental form, and kind of the Higgs bundle data is not that good at giving you that sort of precise estimate in general. Yeah, okay. So we could, yeah. Yeah, so there are, and if it's the same, I guess I know that there's a result of Goldman, Kapovich, and Lieb where they construct surfaces in any integral Toledo invariant, and then they do show that this kind of this convex cocompact, or this discrete case, but at least outside of kind of but they can kind of construct them out of two different sorts of planes. They look at kind of a complex hyperbolic space and a Lagrangian hyperbolic space, and they piece them together to make corners that look like this. And so this construction is actually quite far away from minimal. because you're going to have a 90-degree angle along some kind of codimension 1 thing. So it's not quite clear that we can kind of perturb away from their surfaces that they produce to get something minimal that's close by, or even that it. Yeah. You do have in the case of this sort of convex co-compact representation, then it's a theorem of Goldman and Wentworth that there is an equivariant branch minimal surface, but it's not known. But nothing is known about beyond that. It could actually be branched. It may not, and so it may not be have this nice normal bundle property I was talking about. Okay. Any more questions? All right. Okay. So let me kind of explain a little bit. I mean, at least for kind of the non-experts, kind of what kind of some explanations of the terms. So kind of rho irreducible, this means there are kind of no non-trivially invariant subspaces. And I guess I usually try to think about this. There's kind of a rank 3 bundle, at least up to kind of this group. All right, and I guess, so another thing is I should say a little bit about what is CH2. So CH2, from this point of view, you can think about it as a symmetric space. So PU21 is a real group, and then this is the symmetric space by modding out by the natural compact, which I guess maybe the nicest way to think about this is P of U2 cross U1. And so this U21, this is going to be a Hermitian form of signature. So VW on C3. So this may be V1 W1 bar, V2 W2 bar minus V3 W3 bar. Okay? And so then, so the group, these are going to be all the linear maps on C3, which preserve this form. And so this minus sign means this is non-compact, and then this is kind of the natural maximal compact group. Okay, so this is going to be a symmetric space. So this is of Hermitian type, and so in particular, this is going to be Kaehler. It's going to have a strictly negative curvature. So I guess depending on the normalization, the sectional curvature can be bounded between -1 and -4. And so in particular, there are no flats in this. So this is going to be rank 1. I guess you can actually write down the metric. So in terms of, you can write down a Kaehler form. So so you can write kind of CH2 as a subset of C2, and you could write the Kaehler form as, so I over 2 del del bar log 1 minus norm W squared, where this is just kind of the standard Euclidean norm. And so this is very similar to the formula for the Fubini-Studi metric in CP2. It's just the difference is just a plus here in that case. Okay? All right. And let's see. So I guess one of the main things to explain is what are these divisors D1 and D2. Okay? So I guess in general, you have kind of this map F, which is going to go from disk into CH2, and we're assuming it's not holomorphic or anti-holomorphic. But in particular, we're going to have, we could say that D1, this is going to be the set of anti-complex points. And so this is going to be the space. So this is going to be, say, X in your, I guess I'll I'll do this in terms of the unit disk, such that kind of df at x of the 1, 0 part gets mapped into the 0, 1 part of CH2. Okay? And D2 is similarly the set of complex points. So this is, so where the 1, 0 part gets mapped into the 1, 0 part of CH2. And so kind of the basic facts are that, so these are, so in the situation that we're assuming that F is neither holomorphic nor anti-holomorphic, and is minimal, then kind of the facts in this situation are that D1 and D2 do actually correspond to divisors. And they correspond to, I guess, non-negative divisors. And in kind of a strong sense, in that there is a notion of multiplicity of a kind of a complex or an anti-complex point, which can be measured. So D1 could consist of kind of 2 copies of a single point, for example. Okay? And moreover, that the intersection of D1 and D2, these are just going to be the branch points. So in this case, you can see that kind of the branch points, that's when DF actually collapses. So that's when this is no longer an immersion. All right? And I get there's a theorem of Wolfson that if both of these divisors are empty, then that implies that this minimal surface is Lagrangian. And I guess this theorem of Wolfson, so the setting for this is the theory of kind of minimal surfaces into Kaehler-Einstein complex surfaces of negative Ricci curvature. Okay. So that's kind of a lot of the basic terms here. And so let's let me continue. So Higgs bundles, I guess we'll get to kind of the point of PU21, okay? So in particular, the first thing we're going to start out with is that this map, F, is minimal. And so this is equivalent to, for a map of a surface, this is going to be, 1, harmonic, and also conformal. And then this is one of our starting points, is that harmonic maps, which map into the symmetric space for your group, are closely related to, so this is kind of one of the ways you can kind of think about Higgs bundles. Harmonic maps from surfaces that are equivariant in the right way, which this is, and that map into this symmetric space. Okay? So in particular, kind of F harmonic implies, by a result of Corlett, that F is, I guess you could say, is reductive. And then there are kind of 2 cases. And the main case we're going to consider is that F is irreducible. Okay? And this other case we've already talked about, kind of this strictly polystable case. That kind of simplifies matters because you have an extra splitting. And that's quite strong if the bundle is only rank 3. Okay. So then in this case, we also have kind of a flat connection, which is going to be, so nabla, which may be dA plus psi, where kind of dA is unitary, and psi is kind of typically kind of or it's one version of kind of the Higgs field. And in particular, in this setting, the 1, 0 part of psi is holomorphic, so with respect to the complex structure on D. Okay? And so this is how we're going to get kind of this holomorphic object. All right. So in terms of, so now we kind of, from the holomorphic point of view, this is, this is given by rho. So this is going to be with holonomy rho. Okay. Any more questions? Yeah. No, this is quite general. Yeah. Yeah, so this is just going to be a symmetric space of noncompact type. Okay? All right. So I guess you can similarly, so I've said just a little bit about how you get from the minimal surface to kind of some holomorphic data, but maybe when I start from the holomorphic data side, then, and so for this, I'm going to start with kind of the group GL3C, because I mean, a lot of the proof kind of depends on the specific structure of this group PU21, and so I'll take GL3C. This is just going to be the setting of rank 3 holomorphic bundles. So E is going to be a rank 3 holomorphic bundle over your Riemann over a Riemann surface, and phi is going to be a Higgs field. So in particular, phi is going to be a section over your Riemann surface of the endomorphism bundle of E tensor, the canonical bundle. And so this is naturally kind of, the canonical bundle is kind of like taking a derivative, and this is how it's kind of naturally part of a connection. All right. So then you want to find a metric H on E, a Hermitian metric, such that this same connection, kind of up to kind of a choice of gauge, is going to be the Chern connection plus the Higgs field plus its dual with respect to this, this metric is Yang-Mills. So in other words, the curvature is going to be lambda times the identity matrix on E. So, and so this, of course, in this setting is going to be, or I guess I'm being a little bit sloppy here. So let me kind of write this as if this is kind of the Kaehler form on the surface, this is going to be actually a contraction of the curvature on the surface part, and then we're left with kind of the endomorphism part, which is just going to be a scalar times the identity endomorphism. Okay, and so of course in this works. So this is a version of the Donaldson-Uhlenbeck-Yau type correspondence, and this is due in this situation, and I guess for Higgs bundles on Riemann surfaces, this is due to Hitchin, and except I guess Hitchin's proof was written down for rank 2, but Simpson also kind of did much more general Higgs bundle proofs. Okay? All right. So in particular, in this situation, we're going to have rho, we're going to have a representation, the holonomy of nabla is what's known as projectively flat. So in particular, the curvature of nabla here is not going to be quite just 0, but it's going to be restricted to a very, very small subalgebra of the Lie algebra. Just kind of the identity, just kind of homotheties in GL3R. And so these homotheties, this corresponds to a representation. So let's kind of say this rho. So rho is going to be a representation from pi 1 of the surface into PGL3C, naturally. Okay. And of course, if this were actually flat, then you'd get GL3C. But in general, this is not kind of what you get without some extra data. And so this can be done. So I guess I should write down kind of the condition that's needed for this to work in terms of this theorem of Hitchin and Simpson. So you need kind of, for this to work, you need a stability condition. Okay? And so the stability condition is that for all f, these are going to be a non-trivial holomorphic subbundle of E, which is invariant under the endomorphism action of this Higgs field phi. We want the slope, degree of f over the rank of f, to be strictly less than the degree of E over the rank of E. And so this is kind of the situation that happens in the irreducible case. There is kind of one more case in which you get existence, which is called a polystable case, in which case you have kind of a splitting of this bundle in terms of two subbundles, which are both themselves stable, but they end up having kind of the same slope, these two subbundles. We'll just kind of focus on this one. Okay? All right. Okay, so I should just say kind of this degree situation, just to kind of skip to the end a little bit, this will give us the bounds on the degrees of the divisors. So we have kind of these natural inequalities here, and these inequalities are going to give us these numerical bounds. All right. Okay, so now what I'd like to do is to kind of to consider U21. So in particular, U21 this is kind of the group in GL3 that respects this Hermitian form that I wrote down. And so in particular, you're going to have the Cartan decomposition. So there's going to be a compact part. This is going to be the U2 plus U1, and then there's going to be the P part. And so the P part, that's what gives you the geometry of the symmetric space. And so the P part is naturally going to be, there's going to be a 2 and a 1 here. The P part is going to be here. So the compact part lives in this kind of block diagonal part. The P part is the rest. And the Higgs field phi kind of lives in kind of the P part, at least complexified. Okay? So that's kind of imprecise, but what goes on here is that you have, we're going to have a V is going to be a rank 2 vector bundle, and L is going to be rank 1. So E is going to be, so this actually does give us a splitting of a holomorphic splitting of E into V plus L. V is rank 2 and L is rank 1. And then the Higgs field lives here and here. And so in particular, phi is going to be an element of H0 of Hom from V to L tensor K plus the other part, H0 of Hom from L to V tensor K. Okay? So this is kind of the geometry of Higgs fields on U21. All right. So now what I'd like to do is I want to make kind of a significant simplification here, and that is I want to pass from U21 to PU21. And so with if we have kind of this U21 Higgs field, and you have kind of a nice stable bundle set up, then you get this Hermitian-Yang-Mills connection. And in particular, this is going to be projectively flat. Okay? So when we go to, so we already have kind of a representation of PU21, but this projective flatness means that we actually have a little bit of wiggle room here. We can change the bundle a little bit so long as we still keep the format of this projectively flat thing. And so in particular, we can tensor by, so it still remains kind of the representation remains projectively flat upon kind of tensoring by a line bundle. So this line bundle is going to have some metric on it, and then when you tensor the line bundle, you're going to get some curvature terms which are going to be of this form. And so that's going to remain projectively flat. And so we're going to kind of replace E, which is L plus V, by E tensor L inverse, which is going to be let me write this. Maybe I should say V plus L. I think that's the way I've been writing it. Which is going to be V, so this is going to be a new V, tensor L inverse, plus just the trivial line bundle. Okay? All right. And so in this situation, we get that phi is, so if you just replace this is going to be an H0 of from V. So I'm going to replace L by 1, and I'm going to bring the K into this situation. So Hom from V to K plus, and similarly over here, if I replace L by 1, I'm going to bring kind of a K inverse into this spot, plus Hom from K inverse to V. Okay? So this is going to be the Higgs field in this case. And so in this situation, what we have is this kind of Yang-Mills theory. This gives us this Hitchin and Simpson. This gives us, in particular, an equivariant harmonic map. This is how you construct the, this is going to be essentially the metric that is constructed here, which is going to be harmonic into the space of all metrics, which is the symmetric space. But the minimality condition in addition, this requires that this is going to be conformal. And so what happens is that the condition on here is that, so I guess the Hopf differential, so this is going to be equal to 2-0 part of the pullback of the metric on CH2 must vanish. So this Hopf differential actually has a very nice formula in this case in terms of the Higgs field. This is going to be the trace of B squared. Okay? And so we're going to use this condition in addition to this nice structure of phi in order to get this extension, to kind of recreate V in terms of this sort of an extension. Okay? All right. Yep. Minimality. Well, I mean, the domain has to be a Riemann surface. Yeah. Yeah, one complex dimension. Yeah. Okay. Any more questions? Okay. Okay. So I'm going to write kind of phi as, so this is naturally a sum, so phi1 and phi2 here. And so now I'm going to mess up. And so now I have to put phi1 and phi2 in here. So let's see, kind of if you're going from V to 1, this would mean that you'd send kind of a vector here. So I'm going to write them here, and then this may be, I may have to switch them, but this is kind of the and I want to consider the, there's also a nice formula here. We have formulas for phi1 and phi2. These are going to be, look this up. Maybe I didn't. Let's see where I put that. Okay. So the formula for phi1 and phi2, this is going to be del of f prime, and phi2 is going to be del of f double prime. And so these primes and these dels, these correspond to the different complex structures. So this, let's see, which one is going to be which? So this del, this corresponds to the complex structure on your Riemann surface, and this prime and double prime, this means this is going to be kind of 1, 0 in CH2 and 0, 1 in CH2, the prime and the double prime. Okay? All right. And so these components of the Higgs field can be gotten in terms of just taking various parts of the differential df in terms of the complex structure on the domain and the target. Okay? All right. So let's see. So in particular here, we can find out that the D1, which is going to be the complex points, this is going to be the 0 set of phi1, and D2, this is the anti-complex. Oh, now I think I may have messed that up. So I think these are the anti-complex points, and these are the complex points. This is going to be the 0 set of phi2. Okay? And so I want to consider the situation in which that we're away from these zeros. Or kind of the Lagrangian case where they're both empty. Okay? So away from these zeros, what we have here is we have a map. So let's see which way this goes. So I think I've already kind of messed. Let's see if I've done this correctly. So we're going to have these are going to be maps. So I guess one is from K inverse to, so this will be phi2, and this will be phi1 here in this situation. So V1 goes from, phi1 goes from B to K, phi2 goes from K inverse to V. Okay? And so away from the zeros, so you know these are line bundles, right? And this is rank 2, a rank 2 vector bundle, and these are both rank 1. And the condition that, the minimality condition is that kind of the trace of phi squared is equal to 0. It turns out to be equivalent to, by kind of a nice local computation, equivalent to the fact that this is a short exact sequence of holomorphic bundles. So it's just kind of the trace of phi squared. This corresponds to, you're just composing this phi1 and phi2. That's kind of the only way that phi squared can work under this situation. And when you have this kind of short exact sequence, we're also assuming that we're away from D1 and D2. So these are the places where phi1 and phi2 might be zeros, right? So away from the zeros, you actually have this short exact sequence. And then therefore, we kind of recover V at from K inverse K, phi2, and phi1, and this is going to be as a bundle extension. So typically when you do Higgs bundle theory, you have this holomorphic vector bundle, but you can't pin it down. In this case, you can pin it down. You have kind of the situation where the Higgs field has a nice enough properties, and kind of you use the minimality condition, you can recover V as an extension between these two bundles. Okay? All right. And so these sorts of extensions, where this is kind of considered as an injection into this bundle, and this is a projection. So P1 would be an injection, P2 would be P2 would be an injection, P1 would be a surjection. These are classified by what's known as the extension class, which is just an element of H1 with kind of the tensor product of this bundle tensor the inverse of this bundle. Okay? And in this case, the divisors aren't there yet. Okay? So this is how you can kind of get this structure in the minimal Lagrangian case by Wolfson's theorem, but then kind of putting in D1 and D2. Well, in terms of these Higgs fields, which are holomorphic, you can see why kind of D1 and D2 are going to be divisors of multiplicity. They're just going to be zero sets of some holomorphic object, right? And so in terms of that, if you allow kind of zeros, then this structure is still quite simple. Kind of allowing D1 and D2, then you have kind of this full extension. So A inverse of D1 minus D1, 0. And so this D1, this just means that, well, these are going to, and I think I've kind of messed up my 1s and my 2s, but hopefully this is, which I was kind of worried about. But you can see that kind of a D1 is going to be kind of the 0 set of this one. So maybe I think I have messed up the 1s and the 2s, but so in this case, this is naturally kind of, to take care of the zeros in this sort of algebraic geometry, you just twist by the 0 locus. And similarly, if you're surjecting, you can kind of twist by the negative canonical bundle. Okay? So this is, so you can recreate V in all settings here. Okay? And then you also know kind of to check stability, you consider subbundles of just V plus 1, which are invariant under phi. But phi is kind of built into the construction of V here, right? So these are going to be, actually, this is just going to be a standard injection of bundles, and this is going to be a standard surjection. So it's going to be something like, and again, I may put these in the wrong places. It's going to be in the right frame. This is just going to be this. And so in particular, you can write down all of the subbundles here that are invariant, and you can just check them. And the stability, the slope stability condition, you can compute all their degrees. The slope stability condition is just this. These are the conditions, right? And okay, so that's essentially kind of the proof of the theorem, and I wanted to go through kind of the details here because it really does, it depends quite heavily on the structure of this group and kind of the fact that, I guess, this sort of theory of minimal surfaces into Kaehler-Einstein surfaces where you actually get these sorts of divisors like this. And it would be nice, one of the things we're trying to think about is to kind of extend this to other sorts of minimal surfaces into other kind of symmetric spaces of non-compact type that are equivariant in the same way, but it seems to be a little bit harder. And yeah, so. Where do I use the fact that n equals 2? I need V to be rank 2. That's one of the things, yeah. And because I mean, otherwise, if it's not rank 2, then you have some sort of map like this, but there's no way that it can't be an extension just for dimension reasons. So, so in particular, this is, I think, kind of the motivation for why, part of why this works so well is that for people who know about kind of Higgs bundles and have studied, say, the structure of the character varieties. So character varieties are just going to be where you have rho here and you leave off F. You do this sort of this quotient. then there are kind of some cases which are quite nice. I mean, so if you have kind of a split real Lie group, then that's quite nice. This is, of course, non-split. But kind of the easiest one for people to handle in terms of the non-split real Lie groups are going to be things like SU21 or U21 or PU21. And the reason is that the Higgs bundle theory is most natural in terms of when you relate it to this GL3C. Because I mean, it comes from complex vector bundles, and then there's not that much algebra to get to your real Lie group. Whereas you have kind of an orthogonal group, there's more algebraic structure, which can sometimes be very great, but it also can make things more complicated. So, and also the dimension is quite low here. So, and that's kind of one of the lessons of kind of this sort of higher Teichmüller theory, is that you don't really do kind of the highest Teichmüller theory. You do what could be described as kind of lower middle Teichmüller theory. So you kind of go from PSL2R to PSL3R or PU21, just to kind of you go kind of and that's kind of where, because I mean the larger the group that you get, the kind of the less structure that's going to be accessible. Okay, let's see. Yes, question. Yeah, that's the character variety. That's difficult. I mean, the thing is, what's known is if rho is, so there's a theorem of Goldman and Wentworth in 2007, if rho is convex co-compact, then there exists at least one F. And at least in the Lagrangian case, if we have that rho is kind of close to Fuchsian, then we can show that there is a unique F by using some differential geometry. In the other situations, it's harder to say. And it's kind of, it would be, yeah, so I mean, it's already, yeah. So I guess I should say something about the kind of the character variety, and in this situation, let me just mention kind of one of the original theorems. So there's a theorem of Ja, who will say that kind of the moduli, or the character variety, of irreducible representations of pi 1 of sigma into PU21 has connected components, has all its connected components, say, indexed by the Toledo invariant. And so the Toledo invariant for us, in terms of our divisors, this is going to be 2/3 D1 minus D2. Okay? So we actually get, in our situation, we get a parameterization of where if kind of D1, if the difference D1 minus D2 can remain fixed, but D1 and D2 themselves can vary. And so we have kind of, we get, in some sense, maybe components is too strong a word. We have kind of different pieces of our parameterization which live in the same component of the character variety. And kind of one of the things that is kind of interesting to me now, and that Ian and I are continuing to think about, is the question of, well, we've kind of, this parameterization gives you a natural topology because you can just write down essentially coordinates on everything. And these are kind of quite well understood objects. But there may be some situations where if you kind of let some of this data diverge, so for example, this extension class, this is a vector space, it could go to infinity. If you do that in the right way, I believe that you should be able to limit on some of the other components. Okay? And so in particular, in the minimal Lagrangian case, when D1 and D2 are both 0, we have I've constructed with Wang and Lucia a kind of sequences of these minimal surfaces where we know that kind of some of this kind of Higgs bundle data has to diverge in particular. And I believe that the way this diverges is it's going to kind of concentrate the energy so much that something like a branch point may appear. And if a branch point may appears, if you go from a minimal surface to a branched one, then you produce kind of a D1 and D2 that are both kind of coincide with one point. And that leaves the Toledo invariant. So if this goes from 0, 0 to 1, 1, this Toledo invariant is still. So I believe that there's kind of still some work to do to kind of put this moduli space and kind of relate it to the topology that Jia used as well. And by the way, Jia, I mean, this is kind of one of our sources. He did use Higgs bundles to prove this, and this was kind of one of our sources to learn about Higgs bundles in this setting. I think the F is going to fail to be an immersion. And so I believe that you're just going to, I think it may be possible to go to the case where you move from these divisors being empty to kind of creating, it's like a, I mean, yeah, pairs of points. I mean, this is pure speculation. It's not completely just pure speculation, but it's speculation that you could have pairs of points being created. I mean, I want to say the word bubble, but I haven't. Something is kind of, there's some sort of energy concentration, I believe. But this is kind of not worked out. This is just kind of a speculation. Okay. So, all right. Are there any more questions? So I mean, according to the official clock, I have like almost 4 minutes. So let me just explain a little bit of the case of the minimal Lagrangian case. So the minimal Lagrangian case, so from this setting, this is just where these divisors are both empty by Wolfson's theorem. Then, let's see. The way we consider this is, so what we can do is we can prove there's a kind of an equivalent formulation in terms of a cubic differential. So a cubic differential, this is going to be holomorphic. It just transforms like dz cubed. And by Serre duality, a cubic differential, in the case where these divisors go away, this is going to be equivalent to this, an element of this H1. And so this is going to be the setting. So you do something like this. So gamma is the metric, the induced metric, is, this needs a bar. This is going to be in the same cohomology class of C. So this is how you relate this. And so in terms of this, this cubic differential, so we can kind of solve this. So if the Q is identically equal to 0, which turns out to be the same as the C equals 0 case, then the structure is Fuchsian. And by Fuchsian, I mean that when you develop this plane out, this is just going to be a standard Lagrangian plane in CH2. All right. And with this standard Lagrangian plane, then you can see that the normal bundle is quite nice. You have kind of a normal bundle of Lagrangian planes that are. And so what we do, and this is kind of originally our approach here, is you can perturb Q away from 0. So via kind of Q is equal to some T times Q naught, where T is small. Okay? And so what happens here is you perturb into, for T small, you get some other, so this may be your F of D, But this is going to be what you might call still quasi-Fuchsian in the right setting. And in particular, you're still going to have kind of these Lagrangian normal planes. So this is still convex co-compact. And there's kind of a nice theory in terms of the cubic differentials in terms of when you can kind of find solutions. And so this would be kind of as t gets larger, and we have solutions here. This is going to be the Fuchsian case. And then it turns out we can find a path of solutions that go all the way up to some capital T. Okay? And so this is kind of due to myself and McIntosh, and also to myself and Wang and Lucia. But then there are kind of these other solutions. There's kind of some region out here where there are no solutions. But then there are these other solutions which we don't know, we kind of get from some mountain pass argument using some analysis. So we don't know that these form a continuous family, but there is going to be, at least according to each, there's going to be a dual solution, in some sense, a dual solution up here. And we know that at least in terms of the limb soup, the corresponding metric has to blow up as you approach zero. Okay? So we have these sorts of solutions, and we know that kind of here, in this neighborhood, these are going to be the quasi-Fuchsian ones. But we have kind of all these other sorts of solutions, and in particular, we actually do know something about kind of these limits, and these are the ones for which I believe you may have some sort of interesting, you may kind of get to a minimal surface if you take a subsequence along these limits, which produces a branch point in this situation. Okay, and I should say that this picture was originally done by Uhlenbeck in the situation of minimal surfaces in H3, where the cubic differential is replaced by a quadratic differential. And so in that case, the group is going to be, I guess, P031, but this sort of description, kind of complete description of the minimal surfaces is not known in that setting. Okay, anyway, the thing is flashing red, so I've gone over time, but thank you. Yeah. I mean, he does analyze them. I'm not sure. And I guess these days, I mean, a lot more is known about the connected components of lots of other groups. So I'm not sure which ones are kind of the nicest. Because I mean, there are a lot of nice coincidences here. And to kind of start out, we would think that kind of this H3 case that Uhlenbeck considered would be the easier case. I mean, that's kind of, at least according to the quasi-Fuchsian theory, then that's kind of much more standard. But in terms of the Higgs bundles, this one seems to be more natural. So, yeah. I mean, in this case, there's a theorem of, I'm not sure if it's Toledo and Goldman, that for all the maximal ones in which the Toledo invariant in absolute value is maximal, they're all holomorphic. And they can be, they're all holomorphic and in fact Fuchsian. So they're Fuchsian and in kind of a different sort of Fuchsian here, in which there'd be kind of a complex line instead of a Lagrangian line. A Lagrangian plane. In general, I mean, there are kind of a lot of things known, but I don't know which ones are. Yeah, this corresponds to the cubic form equal to 0, in this, and it's the extension class is 0. So yeah, in this situation. Okay, thanks.